In previous lessons, we've estimated things like area under curves and volumes and all sorts of stuff. Now we're going to talk about how to find the length of a curvy curve. Suppose you want to find the length of a curve that is not a straight line. How might we do this? So we're going to assume we have some curve defined by an equation y equals f of x. And one thing we're going to assume is that this curve f of x is something called smooth. What that's going to mean is that f prime exists. That's a technicality we're going to need to derive this stuff, but just think about the fact that it can't have any corners or breaks, like not like an absolute value or something like a cubic or a cube root, which would have like a little infinite discontinuity in the middle. So we want to find the length from some a to some b. So how long is this curve between this value and this value? And you could think, well, you could theoretically lay like a piece of string down there and then stretch it out and measure it, but that'd be kind of inefficient for things where you had a large function or stuff like that. So you think, there must be a way to do this with like a formula of some sorts. And like many other things, like we did in this class, you start by dividing the interval from a to b up into little pieces. So here's my little pieces. And you say, well, on each piece, I can approximate each piece by a straight line, because you can find lengths of straight lines. So what I'm going to do is I'm going to define the distance between 2 points. We'll call this, like, that's p sub 0, this is p sub 1, this is p sub 2. These little bars are going to mean the distance between p sub I minus 1 and p sub I. So that is the distance from p sub I minus 1 to p sub I. And let's talk about how we might calculate that. So this little distance, you can calculate it using the Pythagorean theorem. So this little distance is delta x, the little vertical distance is delta y. So that p sub I minus 1 to p sub I is going to be equal to the square root of delta x squared plus delta y squared. And if we add up all of those little pieces, we're going to get an estimation for how long our curve is. And delta x is constant, but delta y is changing. Like the delta y for that first piece is going to be different than the delta y for this next piece. And what it is depends on the curve. So here is how we're going to figure out what that delta y is. We apply the mean value theorem, so from calculus 1, MVT, on the interval x sub I minus 1 to x sub I. And what that tells us is there is some x sub I star in the interval from xi minus 1 to xi. And at that point, the derivative, f prime of x sub I star, is equal to the slope of the secant line, which is given by f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. And you should be thinking like, well, what the heck? Why is that useful? And the reason that this is useful is because f of x sub I minus f of x sub I minus 1 is the difference in the y values, as in the y value at the second endpoint minus the y value at the first. That is the same thing as delta y. Similarly, the denominator, x sub I minus x sub I minus 1, that's the difference in the x's, or delta x. And that tells you that delta y is equal to derivative at some sample point, don't care which one, delta x. And this tells you the relationship between the change in y and the curve itself. So a little random piece, pi minus 1 to pi, will will be equal to the square root of delta x squared plus f prime x sub I star delta x, that quantity squared. And notice that both components underneath that radical have a delta x that's squared, so you can factor it out and square root it. And we get root 1 plus f prime of x sub I star, the quantity squared, delta x. And that tells you the length of just one piece. So your total length is going to be about equal to a sum from I equals 1 to n of all these pieces. And if you want to find it exactly, you take a limit of that, n goes to infinity, this makes this into an integral, and your length is equal to an integral from a to b square root 1 plus f prime of x dx. Oh, squared. So that formula is how you find the length of a curve. You take your curve, you take its derivative, you square it, add 1 to it, integrate the square root of that quantity. So if f prime is continuous on the interval from a to b, that is that whole business about the curve having to be smooth. The reason that that is true is because we had to apply the mean value theorem, and we couldn't do that if we couldn't talk about the derivative. Then the length is given by the integral from a to b square root 1 plus f prime of x squared dx. All right, let's find the arc length of y squared equals x cubed between the points 1, 2, and 4, 8. So first of all, let's solve this for y. Y is equal to x to the 3 halves. So between this point and this point. So our length formula is the integral from a to b square root 1 plus f prime of x squared dx. So let's find y prime. Y prime will be 3 over 2 x to the 1/2. All right, and the values here in our integral are x values. So from 1 to 4, square root 1 plus 3 over 2 x to the 1/2, the quantity squared dx. So we've got the root 1 plus 9/4 x dx. And if you're actually asked to solve the integral, most of the problems are doctored to work out pretty well because often these integrals are really complicated and aren't solvable with normal techniques. This one we can solve using a u substitution. So we'll let u equal 1 plus 9/4 x. du is 9/4 dx. Change your bounds. If x equals 1, u is 1 plus 9/4 or 13/4. And if x equals 4, this implies u is 1 plus 9 or 10. So this becomes the integral from 13/4 to 10. We'll have 4/9 as a coefficient because we had to solve that for dx. U to the 1/2 du. So that's 4/9 times 2/3. U to the 3/2, evaluated from 13/4 to 10. I'm so sorry, but the numbers are not very nice. So that gives us 8/27, 10 to the 3/2 minus 13/4 to the 3/2. And 10 to the 3/2, that's the same thing as 10 to the 2 over 2 times 10 to the 1/2, or 10 root 10. So 8/27, 10 square root is 10, minus 13/4 square root 13/4. And you can't root 13, but you can root 4. So you have 8/27 times 10 square root 10 minus 13 over 8 root 13. And that's good enough. Your textbook did this problem, and what they did was distributed the 8 because that made the 8 in the denominator cancel. So they said it was 1/27 times 80 root 10 minus 13 root 13. Either one's okay with me because the arithmetic isn't the important part. The important part is, can you set it up and do the u substitution correctly? All right, so find the arc length of the curve y equals ln of cosine x between 0 and pi thirds. So let's just start by figuring out what f prime is, because we're going to need that for the formula. So you have to remember the chain rule. The derivative of ln of something is 1 over the something times the derivative of the something. So that will be negative sine x over cosine x. And our length will equal integral a to b square root 1 plus f prime of x squared dx. So 0 to pi thirds root 1 plus. Now sine over cosine is tangent. So you have negative tangent of x. When we square it, the negative goes away. We just get 1 plus tan squared x. And then you have to remember that 1 plus tan squared is equal to secant squared. And then you say, okay, well, I square root secant squared and I get secant. And I didn't make you memorize the formula for the antiderivative of secant, but by now you know it. It's ln absolute value secant x plus tan x. So that's ln absolute value secant of pi thirds plus tangent of pi thirds minus ln absolute value secant of 0 plus tangent of 0. And you're in Calculus 2, there is absolutely no reason that you should not understand how to use the unit circle. If you don't know, you need to get some help, you need to YouTube, you need to ask me or somebody else. So pi thirds is this angle. And at that angle, the coordinates of the points are 1/2 root 3 over 2. The first one is the cosine, the second one is the sine. So secant is 1 over cosine, so you have 1 over 1/2, which is 2. And pi thirds, tangent at that point, is sine over cosine, so root 3 over 2 over 1/2 will just be root 3. At that point, at 0, which is right there, the cosine is 1, the sine is 0, so secant of 0 is 1 over cosine of 0, or 1. Tangent of 0 is 0 over 1, which is 0. Natural log of 1 is 0, so the answer here is ln absolute value 2 plus square root 3. Sometimes the curves that work out for arc length and work out well look a little bit nasty before you start taking derivatives. So here's an example of one of those. This probably won't show up on a test, but it might show up on a homework assignment. So find the arc length to the graph of this particular curve between 1 and 2. So first let's figure out what y prime is. So rewrite y as 1/6 x to the 5th plus 1/10 x to the negative 3rd. Y prime will equal 5/6 x to the 4th minus 3/10 x to the negative 4th. Or 5/6 x to the 4th minus 3 over 10 x to the 4. All right, and also we're going to have to square y prime, so I am just going to find y prime squared right now and then use it. So that is 5 over 6 x to the 4th minus 3 over 10 x to the 4th multiplied by itself. And multiplying that out, we get 25 over 36 x to the 8th minus 15 over 60, those x's cancel, minus another 15 over 60, plus 9 over 100 x to the 8th. That's the same thing as 25 over 36 x to the 8th minus 30/60ths, or 1/2, plus 9 over 100 x to the 8th. And just for future reference, just remember that that came from 5 over 6 x to the 4th minus 3 over 10 x to the 4th, that whole thing squared. Now to find our length, we integrate from a to b, square root 1 plus f prime of x, the quantity squared dx. So that's the integral from 1 to 2. Now think about what happens when you add 1 to this expression. So if you add 1 to this, when you do that, you get 25 over 36 x to the 8th plus 1/2 plus 9 over 100 x to the 8th. And believe it or not, that stuff inside the square root sign, notice how this thing we had came from 5 over 6 x to the 4th minus 3 over 10 x to the 4th quantity squared. This is going to be the exact same quantity with a plus instead of a minus, the only difference. So it'll be 5 over 6 x to the 4th plus 3 over 10 x to the 4th, the quantity squared dx, which then ends up being square rootable. So this is the integral from 1 to 2, 5/6 x to the 4th plus 3 over 10 x to the negative 4. And even though these problems work out, they're still a little bit gross. So I care that you can anti-differentiate. When you do so, you get 5/6 x to the 5th over 5 plus 3/10 x to the negative 3 over negative 3, evaluated from 1 to 2, or x to the 5 over 6 minus 3 over 10 x cubed, evaluated from 1 to 2. And from there, you get, after lots of arithmetic, you get 1,261 over 240. Don't waste your time doing that arithmetic. Just make sure you understand the whole factorization process. An occasion in this chapter, you're going to run up against other integration techniques that you have to use, the ones that we learned in chapter 7. So find the exact length of this curve between x equals 0 and 1/2. So y prime, not so hard. It's negative 2x over 1 minus x squared. So my length will equal an integral from 0 to 1/2 square root 1 plus that thing squared, which will be 4x squared over 1 minus x squared, the quantity squared. And you think, if nothing else, what you can do inside that square root sign is get a common denominator. So the common denominator is 1 minus x squared, the quantity squared. When you expand that out, you get x to the 4th minus 2x squared plus 1, and then plus the 4x squared from the other numerator, which is the same thing as square root x to the 4th plus 2x squared plus 1. In this denominator, we can make this into 1 minus x squared, because we can square root away that squared. And also notice that the numerator is x squared plus 1, the quantity squared. So we're at the point where we're at 0 to 1/2 x squared plus 1 over 1 minus x squared dx. And you think, whoa, partial fractions. And unfortunately, you have to do two things. You have to first do long division, and then you have to do the partial fraction. So I'm going to divide my page into a couple pieces, and over here on the side I'm going to do the long division. So we're dividing negative x squared plus 1 into x squared plus 1. So what multiplies to negative? What do you multiply negative x squared by to make it match x squared? And the answer is negative 1. Take it away and you get a remainder of 2. So that tells us that thus far we have an integral from 0 to a half negative 1 plus 2 over 1 minus x squared. And then even though you can integrate that first term, you have to worry about the second term now. And that's the same thing as 2 over 1 minus x times 1 plus x. And you must do partial fraction decomposition on that. So 2 over 1 minus x times 1 plus x is a over 1 minus x plus b over 1 plus x, which is the same thing as saying 2 equals a over 1 plus x, b times 1 minus x. Now, this is an easy one, as in when you input x equals 1, you get that a has to equal 1. And when you input x equals negative 1, you get that b has to also equal 1. So this gives us the integral from 0 to a half negative 1 plus 1 over 1 minus x plus 1 over 1 plus x dx. And that's something we can actually handle. So anti-differentiate, we get negative x plus ln absolute value 1 minus x plus ln absolute value 1 plus x. Evaluated from 0 to a half. So that's negative 1 half plus ln of 1 half plus ln of 3 halves. Inputting 0 gives us 0 in every case. So there is your arc length. Things probably won't get that complicated on like a timed quiz or a timed test, but there may be homework problems that you have to do that are that hard. So just be aware that you have to know or recognize that you may have to use other integration techniques. Now often you might care to find the arc length function, as in you have a certain starting point and you want to find the length from that starting point to any ending point. And so how you denote that is this. You have your integral and you go from a up to your value x. So the a point is a fixed point, and inside the integral you replace the x with a different variable. In this case, use something like t, f prime of t squared dt. And evaluating this is going to get you an equation that you can then plug any x into. So find the arc length function for the curve x squared minus 1/8 ln x, and then take p sub naught is 1, 1 as the starting point, and then approximate the length from 1, 1 to 3 and whatever f of 3 is, which will be 9 minus 1/8 ln 3. So first of all, f of t is going to be equal to t squared minus 1/8 ln of t. F prime of t will equal 2t minus 1 over 8t. And so my arc length function will equal an integral from 1 to x, and then square root 1 plus f prime of t squared dt. So 1 to x root 1 plus, now when I square out that expression, well, I've got 4t squared minus a quarter plus 1 over 64t squared. That minus 1 quarter makes negative 1/2, which plus that 1 makes positive 1/2. Another one of those tricky factoring things. 4t squared plus 1/2 plus 1 over 64 t squared. And that will factor into 2t plus 1 over 8t, the quantity squared. And now the square root can cancel with the squared. We have the integral from 1 to x 2t plus 1/8 times 1 over t dt. Now anti-differentiate, and we have this is t squared plus an eighth ln t, absolute value, evaluated from 1 to x. And that's going to be x squared plus 1/8 ln absolute value of x minus quantity 1 plus 1/8 ln of 1, but ln of 1 is 0, so our arc-like function is x squared plus 1/8 ln absolute value of x minus 1. So that tells you the length of the curve x squared minus 1/8 ln x from 1, 1 to some other point x f of x. To find the length from 1 to 3, all you have to do is plug in 3. So s of 3 will equal 3 squared plus 1/8 ln of 3 minus 1, which is 8 plus 1/8 ln of 3. In many cases, the integral that results from setting up an arc length problem is difficult or impossible to find using integration techniques, and as a result, approximation methods such as the midpoint trapezoid and Simpson's rule are used. So we're going to use Simpson's rule with n equals 10 to estimate the arc length of y equals e to the negative x squared for x between 0 and 2. So first let's set up the integral. So f prime of x, or y prime, will equal negative 2x e to the negative x squared. That thing squared, because we're going to need it, is 4x squared. Now when you square something to a power, those exponents multiply. Like think, for example, x squared to the 5th is x to the 10th. So that becomes e to the negative 2x squared. So your arc length is an integral from 0 to 2 square root 1 plus 4x squared e to the negative 2x squared dx. So this is the thing that you need to estimate. All right, Simpson's rule with s equals 10. First, let's find delta x. Delta x will be 2 minus 0 over 10, or 1/5, or 0.2. And let's define g of x to equal the thing inside the integrand. So root 1 plus 4x squared e to the negative 2x squared. So then our length will be about equal to Simpson's rule with 10 pieces, which recall is delta x over 3, so 0.2 over 3. And we have 1 g of 0 plus 4g of 0.2 plus 2g of 0.4 plus 4g of 0.6, and it keeps going forever and ever, plus 2g of 0.8 plus 4g of 1, 2g of 1.2, 4g of 1.4, 2g of 1.6, 4g of 1.8, and then finally a singular g of 2. And holy moly, I don't know why they always give you n equals 10, because that's super tedious. That's approximately equal to 2.28053. So the final question we're going to go over is an application of arc length to engineering. And we're going to use calculators because engineers are going to use calculators to do their computations. So suppose you want to make some metal roofing, and the panels that you produce are going to be sort of like curvy, and they are going to be 28 inches wide and 2 inches high. And you produce them by processing flat sheets of metal. So the profile that this roofing takes is a sine curve. So we're going to verify that the sine curve has this equation. And we're going to find the width of a flat metal sheet that's needed to make this 28-inch panel. So that is going to be equivalent to figuring out what is the arc length of that piece. If you find that length, you figure out how long the piece needs to be before compressing. So let's draw that curve on the x and y axis. So we're just going to look at that one-dimensionally for now. So ends at 28. It appears to me, it's a little bit hard to see, I think that goes through 2 cycles of sine. It goes up, down, up and down, and then up and down. So halfway at 14, then halfway at 7, and then 21, and it goes up to 1, down to 7, down to -1, and then repeats that pattern twice. So they told you what the curve is, and in real life that might not happen, so you've got to figure out how would you come up with that curve on your own. So first of all, assuming your curve starts at 0, you know it's going to be a sine curve. So what you've got to figure out is there's some number in front and some number inside with the x. So this number describes how far up or how far down the sine curve goes. So the total distance from top to bottom of the curve here is 2. Now, a regular sine curve also has a distance of that being 2 from top to bottom. So in this case, that a is just equal to 1. A is often referred to as the amplitude, which is half of that total distance. Now to figure out what that k is, you know that k times x has to equal 2 pi when x equals 14. So it takes 2 pi for sine to go through one cycle, and so in this case that happens after you hit 14. So k times 14 equals 2 pi, and that tells you that k is 2 pi over 14, or pi over 7. So that is the equation that they gave you. The equation of this is going to be 1 sine pi over 7x. And all we have to do now is find the arc length of that on the interval from 0 to 28, which, given that you have a calculator, shouldn't be super hard. So first, let's find y prime. Well, it's going to be pi sevenths cosine of pi 7x. And so the length of your curve will be an integral from 0 to 28 square root 1 plus that quantity squared. So pi squared over 7 squared cosine squared pi over 7x dx. And you're supposed to evaluate this with a calculator. I don't need you to work this out by hand. It's not necessary, nor I don't think is it very likely it's going to work out pretty. And this is approximately 29.3607. And just do a little bit of a check, does that seem reasonable? And I think that it does, because it certainly is the case that this width is going to need to be more than 28, because when you smush it into that wavy shape, you're going to lose some length. So there's an application in engineering, and what you might have to do in engineering class is actually get the whole sine curve yourself, and that part can be a bit tricky, and then know how to set up the integral to find the length.